So continuing on with the last lecture and talking about carboxylic acid and its acidity, we finished with saying that the OH groups are the most acidic in this structure. So if that is the case, then how do we know which OH is the more easily removable or the most acidic proton present? So let's look at OHs, and I have three OHs, and there are this OH is part of a carboxylic acid. This OH is on a phenyl group, so it's a phenol, and this one is just a regular acid with an R group attached, so it's a regular alcohol. And if you look at the pKa of these three class of compounds, the pKa of this is around 4 to 5, and pKa of the phenol is around 10. pKa of the cyclohexanol is around 16. Alright, so one question that you might have at this point is why, if all these three hydrogens are attached to oxygen, why do they vary in their pKa? So just looking at the pKa, we know that the carboxylic acid proton is the most acidic or most easily removed by base, and that's this pK is very standard for carboxylic acids. If you look at carboxylic acid functional group in general compared to all the other organic functional groups, they have the lowest pKa. So that means carboxylic acids in general, okay, so this is an important thing to remember, that the carboxylic acids in general are, we could consider them as organic acids. All right, so if you're comparing to, you know, sulfuric acid or hydrochloric acid, the inorganic acid, this is no way near acidic as those. But if you only compare organic compounds, you'll see that the carboxylic acids are the most acidic of organic compounds. So therefore, it has I guess it has a propensity to lose a proton readily. And the proton that it loses when it's faced with the base is that proton. All right. So let's now look at the Y. All right. Why is the carboxylic acid proton much more acidic than the phenol proton and a cyclohexanol proton? All right. I believe you went over this with in Chem 114. But I just want to briefly go over the reason. And the reason for this is that when a carboxylic acid loses a proton to a base, and it forms a carboxylic acid salt, okay? So let's say you react with sodium hydroxide, then it would be a sodium salt of carboxylic acid. And by the way, these deprotonated type of carboxylic acids are named differently. So you name the sodium, the metal first, and then whatever the acid would be, instead of using oic acid, it ends in ate. Okay, so sodium, for example, acetate. Notice the 8 ending. So that would be the name if R was CH3. All right. So instead of acetic acid, it would be an acetate. If this was a 3-carbon long one, then instead of propanoic acid, it would be sodium propanoate. So it would have an 8 ending with a metal name in the front. All right. So when you look at these acid salts, they're called, you have to look at the equilibrium of, you know, when this proton is removed, how stable the product is. And when you look at this carefully, notice that the oxygen, there's 2 oxygen sharing the negative charge, So you could draw a resonance structure in which you have the negative charge there and a double bond here, okay? So what does that mean? The negative charge that you created by deprotonating this proton is equally shared between the two oxygens, and you know that the oxygens are electronegative. So that means the salt that you created is pretty stable, which means that it is willing to give up the proton because it's forming something stable, all right? So this proton doesn't mind losing the proton because it knows that it's going to have resonance stabilization with the other oxygen. The flip side of that is if this is removed with the base, then notice here you form an alkoxide, but there's absolutely no way to stabilize this O minus, okay? So no resonance. This oxygen negative charge is stuck on that oxygen and that's it, all right? There's no way to stabilize, all right? So comparatively speaking, this hydrogen is much easier to remove than this. All right, and that's reflected in the difference in the pKa. All right, why the acid pKa is so low compared to the cyclohexanol. The flip side of that is, so then this phenol, when this gets removed, you have a phenoxide. All right, now why is that in between? When you know you could draw a resonance structure, as you've done many times. Oops, so not this one, this one. You could draw a lot of resonance structures, right? And you could draw one more, all right? So you could argue that this has a lot of resonance structure, so why is this pKa higher than this one, okay? Now, even though you could draw a resonance structure, look at the resonance structure that you're drawing. Where are you putting the negative charge? You're forcing it in the ring on the carbon atoms inside the benzene ring, right? Whereas over here in carboxylic acid salt, you're putting the negative charge equally between the two electronegative oxygens. So what does that mean? This is going to be a lot more stable of a resonance contributor than these, even though it does have some stabilization because of the sp2 orbitals in the benzene ring, right? So there's a resonance stabilization throughout the ring. That's why it's lower in pKa than the one that doesn't have any resonance stabilization at all, but it's going to be higher than a carboxylic acid. All right. So the upshot of this is that the organic acids, all right, because it could form a resonance with another oxygen, when this is removed, carboxylic acids function as the organic acids in the way it behaves in its functional group. All right. So another way to look at this is a trend set here where you have a carboxylic acid, and here you have 3 chlorines next to it, and you have 2 chlorines next to it, 1 chlorine, and no chlorine. Okay, so this is basically an acetic acid, and that pK is 4.76. As you put a negative charge, electronegative atom next door to this, notice that the pK goes down and down and down. Okay, that's because due to inductive effect. So this is not a resonance through resonance or anything like that, but when you have when you're deprotonating and you have something here next door that is electron withdrawing group, what it's doing is through sigma bond is withdrawing electron density towards it. And that's what the chlorine is doing, thus inductively stabilizing the negative charge. Okay, so even though they're all carboxylic acids, by having 3 electronegative atoms connected on the next door carbon, it causes this charge to be even more stable. All right, and you could see that trend in your book, where if you have a long carboxylic acid, if you put a chlorine here, is lower in pKa, but if you put a chlorine here, the pKa goes up, and if it's over here, it's slightly even more, etc., etc. So further away it is from the carboxylic acid, it has less and less effect. All right, so take a look at the difference in where the chlorine is in terms of pKa. All right, and the last trend that I want you to take a look at is in benzoic acid. So once again, you have benzoic acid in all 3 cases. The only difference is on the para position, the substituents that are attached to the benzene ring. All right, and it seems like it should be too far away to have an effect, but you know from the aromatic chemistry chapter that the substituents on the benzene ring does have an effect through resonance. So you need to classify each one of these as to whether or not it is an electron withdrawing group or electron donating group, and then that will determine whether this negative charge that you create on the carboxylic acid is going to be stabilized or not stabilized, and that will create whether or not the pKa is going to be lower or higher. So which of these 3 do you think is going to be the most acidic? All right, so if you remember from the benzene chemistry, you know that nitro group is a very strong electron withdrawing group. All right, that's because this nitrogen has a plus charge if you draw out, so it's sucking electron density towards it. All right, whereas the methoxy group has an electron donating effect because of the lone pair on it that could distribute. So this is slightly electron donating group. And then chlorine is, remember, electron withdrawing group, and not a very strong electron withdrawing group, but a weak electron withdrawing group. And that is sort of predicted when you analyze these substituents, because if you look at the pKa, this is at 3.4, this is at 4.5, and the pKa once the chlorine is around 4.0. All right, so notice that the most acidic is the one with the nitro group substituent on it, and then the chlorine, followed by the methoxy group. All right, so these trends you should be able to use in answering questions like 20.9, 21.4, and 21.39. I expect you to do those before the next lecture.